So good evening everyone. Today we will be discussing about Raman spectroscopy. The name Raman is because of the name of the great scientist from India, Dr. C.V. Raman. So he developed what do you call he developed the principle of this spectroscopy, and he demonstrated that uh, the molecules also, just like electronic configurations, they can also uh, give some spectra. Okay, so over here what happens in the Raman spectroscopy, basically we look into molecules. Say there is a atomic molecule, and we make an electromagnetic radiation incident over the molecule, and then we look into the scattering induced by this molecule. So this molecule, diatomic molecule in this case, it can interact with the electromagnetic radiations in three possible ways, which we'll be discussing in later part of this lecture. And over there we can see the manner in which it interacts. That has some mechanics, and that mechanics was first proposed by by Dr. C.V. Raman, and due to this spectroscopic technique, invention of this spectroscopic technique, Dr. C.V. Raman, he got the Nobel Prize. Okay. So in this case, it is slightly different from the UV visible spectroscopy. In the UV visible spectroscopy, we have discussed about the electronic transitions. And also in the last class, we have discussed about fluorescence and phosphorescence. Okay. So in UV visible spectroscopy, in fluorimetry, in phosphorescence spectrometry, in all these things, we basically discuss about the electronic transitions. In the case of Raman spectroscopy, it is not the case. It is not the electronic transitions. It is basically the molecular transitions which take place. Okay. So let us understand the mechanics of this one. Suppose in Raman spectroscopy, what we do is that we have a light source which is basically a laser. Okay. And we all know that this laser, it is having a high density of energy. And it moves in a straight line. Okay. In contrary to the Raman spectroscopy, if you consider the previous spectroscopic techniques, we had polychromatic light sources. Okay. We had polychromatic light sources. Now, thereafter, we used a series of optical systems, say gratings or the monochromators, to convert the polychromatic light into a monochromatic light. Okay, and then we were exciting the sample, and then we were looking into the interaction of that monochromatic light with the sample. Okay. In fluorescence and phosphorescence, we were using monochromatic light, right? Now over here we can either use polychromatic light sources, or we can also use laser sources if you want to have a specific wavelength fluorescence fluorimeter or the phosphorescence spectrophotometer. Okay, we can use a specific wavelength laser source also in fluorimeter and phosphorescence spectrophotometer. We can either go for the polychromatic sources or we can also go for the laser. However, the condition is that we have to incident a monochromatic light onto the sample. Okay. Now, after the interaction with the sample, over there at a 90-degree angle, we were measuring the full spectra. Right? We were measuring the full spectra. This is in the case of fluorescence or phosphorescence. Okay. In the first case, in the UV visible spectrophotometer, I was talking about the conventional spectrophotometers. Okay. However, in the case of imaging based spectrophotometer, I'm writing it in short. Okay. In those cases, we are using the polychromatic light. Okay. Please keep this in mind. What kind of light source is being used in different types of spectroscopic techniques. Okay. Otherwise, I can give you during the exam, I can give you a comparison of give a comparison between the say fluorescence spectroscopy and UV visible spectroscopy and like that. Okay. So for this, you need to have a proper understanding about all of this. Okay. As I was telling, coming back to this Raman spectroscopy. So herein we are having a monochromatic laser source. Which will generate a laser of a specific wavelength, and that wavelength, it is basically called the excitation light, having a frequency of mu0. Now that is being made incident onto a molecule. In this case, we have shown a diatomic molecule. Okay. Now, why diatomic molecule? We have just taken it for the convenience of our understanding. It is not like that the other molecules will not show the Raman spectra, but for the convenience of our understanding, we are just considering a diatomic molecule. Now, what does this spectroscopy do? This spectroscopy, it helps us in analyzing scatterings. Scatterings from the molecules. Okay. This spectroscopic technique helps us to analyze the scatterings from the molecules. Okay. So scattering of what? Scattering of the electromagnetic radiations. Okay. Electromagnetic radiations. So what happens over here? Consider our your lower level classes. Suppose you are having a matter. You are sending a H mu naught radiation, electromagnetic radiation. We can also call it in the particulate form as photon molecules. No, not photon molecules, photons. Okay. So we are bombarding this matter, this red color matter, with photons. When this photon interacts with this matter, what it may do? There are three, what you call, there would be three ways how this photon will be interacting with the matter. What are the three ways? The first way will be, it will be scattering this molecule in such a way that there is an elastic scattering. Okay, that means in elastic scattering we have the energy of the incident radiation, it is equal to energy of the reflected or the scattered radiations. Okay, so in this case we will be having h of mu equals to h of mu naught equals to h of mu naught. H of I, it would be h of mu naught, which would be equals to h of mu naught again. So herein there is no loss of, that means with whatever photon you are bombarding the material, that material, it is not keeping some energy or getting some energy from that photon, nor it is giving any energy to that photon, and the photon is being scattered in an elastic manner. So there is no loss of energy in that type of scattering. In the second case, it may so happen that the scattered radiation over here, h of mu naught, it is, what is it? No, what it is? It is nothing but the energy. So the energy would be reduced by an delta E fraction. Okay. So the scattered radiation, it would be the energy of the scattered radiation, it would be reduced by a fraction of delta E. Okay. Third possibility, this is the first possibility. Second possibility is it would be reduced, and when it is being reduced, it is called Stokes phenomena. Which results in the Raman shift. Okay. In the third case, here also you will be having h of mu naught, but the matter will impart, in this case, in the third case, the matter will impart some energy to the photon, and there will be a gain of some energy. Okay, and this is called anti-Stokes phenomenon. Okay, and it also results in the Raman shift. Are you getting my point? While I have discussed all these things, please be remembered that herein I am talking about molecules. Please do not confuse this Raman scattering with the Compton effect, which are being shown by the electrons. Okay. In Raman scattering, we are only talking about the molecules. Herein the scattering are being imparted by the molecules, not the electrons. Okay. Now this Raman scattering, as I told that this is a diatomic molecule we are talking about, it may have vibrational energy. Secondly, it may have rotational energy. no, vibration and rotational energy. Energy means energy levels. Okay. These diatomic molecules, they may have either vibrational energy levels or they may have rotational energy levels. Okay. Rotational energy levels, they are being shown by diatomic molecules which are having some dipoles. Okay. And when they are rotating, they are creating some magnetic field. Okay, because dipole, it is nothing but a magnetic vector. So all the magnetic vectors, they are associated with magnetic field first, and second is the electric field. And when we are incidentating an electromagnetic radiation over here, what it is doing? Electromagnetic radiation, it is having its own magnetic field and electric field, and accordingly it is interacting with this thing, and whatever the scattered radiation is there, you are getting results as per that. It may positively interact with this magnetic field and the electric field, or it may negatively attract. Okay, if there is a reduction in the energy, then it is called Stokes phenomena, and if there is an increase in the energy, then it is called anti-Stokes phenomena. Okay, similarly, the second way these diatomic molecules, it may behave is that there is a bond, it will start vibrating towards each other and again going away from each other. Okay, so the larger the energy, the higher will be the frequency of moving towards each other and going back. That means the faster will be the vibrations. Lower the energy, lower will be the vibrations. Okay, so herein, when we talk about Raman effect, in the Raman effect, we have a combinatorial interaction of the energy levels of both vibrational and the rotational energy level in the rotational energy levels. Okay, so you please keep it in mind. For the sake of understanding, easy understanding, I will just be calling these levels as energy levels in my subsequent lectures. Okay, are you getting my point? Now herein, there is another important thing which you should keep in mind. There are certain formulas. We know energy is equal to h mu. What is mu? It is nothing but hc by lambda. Okay. Then we have another this thing. This lambda is wavelength. This mu is frequency. Frequency is given in hertz or second inverse. Wavelength, it will be in, say, usually nanometers scale. Okay, it can also be given by E equals to hc mu bar. What is this mu bar? Mu bar is nothing but the wave number. And it is given by, wave number is given by 1 by lambda. Okay, wave number is given by 1 by lambda. Okay, I hope you have understood this thing. Now you have to keep in mind over here, energy is directly proportional to the mu and it is also directly proportional to the wave number. Okay. On the contrary, energy is inversely proportional to the wavelength. Now, if you look into the wavelength scale, in the wavelength scale, if you see a typical Raman shift, it starts from higher value to lower value. Okay, as we go towards the right. Conventionally, if you want to plot anything, what you get? We get on the left hand side the lower value, and on the right hand side we get the higher value, right? Whatever be the thing, say x parameter. In the case of Raman scattering, when we are dealing with wavelength, when we are plotting the Raman scattering in terms of the wavelength, we are having higher value on the left and lower value on the right. But if you see, wavelength is inversely proportional to the energy. Wavelength is inversely proportional to the energy. Okay, that means if we plot energy, we will be having higher E over here on the left hand side and lower energy on the right hand side. Okay. Further, E is directly proportional to frequency. So we'll be having high mu. Sorry. Wavelength is higher. So here your energy will be lower. So we are having, when your wavelength is high, your energy is low, and we are going towards the high energy. Our frequency is low and we are going towards the higher frequency. Okay, so you please keep it in mind that when we are plotting the Raman scattering plot, we are basically interested in analyzing the energy. Okay, how the energy content is being changed. Okay. So from the left hand side to the right hand side, we get lower energy to the higher energy. Okay. Also, we have discussed about this wave number. What is the unit of the wave number? Unit of the wave number is centimeter inverse. So Raman shift can also be given by wave numbers, where on the left hand side you will be having this you will be having lower wave number, and here we will be having higher wave numbers. Okay, as we go to the right hand side. Now in the plot, suppose we are making an laser of 532 nanometer incident over here, okay, onto this molecule. So let me draw this what do you call the energy levels, where n is equal to 0, 1 and 2. Okay, so we have a molecule over here. At the top level, we can have virtual level. We are having virtual level. So what happens when you are making a light incident onto the molecule h of mu naught, then this molecule, it may gain energy and it will go to a virtual level, which is at a high energy level, and immediately it will release the energy. Okay, when it is coming from the upper level to the lower level, what it is doing? It is releasing the energy, and see, it has neither gained any energy nor it has released extra energy. So in this case, whatever the energy it has gained, it is releasing the same amount of energy. So over here, if you say it has, you have bombarded the molecule with 100 photons, it is releasing 100 photons while it is coming back to the low energy state. Okay, so the peak, what you will be getting, it would be a very sharp and high peak, and that peak it is regarded as Rayleigh scattering. That peak it is regarded as Rayleigh scattering. Okay. In the second case, let us take this ground energy levels again. Now, while coming back, it comes back to the level n equals to 1. Okay. So what is happening? Suppose here you have bombarded with 100 photons. Here is it is not coming down to its original level. So basically, this molecule is retaining some energy. Energy is retained by the molecule. So say for example, it is retaining energy equivalent to 20 photons. So how many photons it will radiate, or it will scatter? It will scatter 80 photons. So what is happening? The energy will be decreasing. Okay, the energy of this radiation will be decreasing, and herein this energy lost, it will give you information about this energy levels. What is the difference between each of the energy levels in the molecules? Are you getting my point? On the other hand, there can be another situation. So this happens when there is a Stokes shift. Why shift? Because say we have performed this for the with a 532 nanometer laser, and from there we have to calculate this shift. So okay, so suppose for a typical diatomic molecule, it would be the 532, this thing, and you will be getting a line over here. And since we have seen that on the left hand side we have a lower energy, so we'll be having the Stokes line. This is called Stokes line. And the shift in terms of the wavelength, it is called Stokes shift. Okay, in terms of wavelength, in terms of frequency, you can also say, okay, or in terms of this wave number also you can depict the Stokes shift. Okay, so what is this distance it is telling? The distance between the Stokes line and the Rayleigh scattering line, what it is telling? It is telling, or it is giving you the information about energy the energy between the two levels. Okay, are you getting my point? Now, as I told you, in the third case, what would happen? Again, we are having three levels. We are having virtual level. But now, suppose that your ambient temperature is hot. So what it will do? Already your molecule has moved from energy level of n equals to 0 to n equals to 1, and from there it goes to the virtual level. And then from there it comes back. But when it comes back, what happens? It comes back to the lowest energy level. Okay, it comes back to the lowest energy level. So herein what is happening? While going back, while going from the ground level to the virtual level, suppose it has taken 100 photons, but when it is coming back over here, up to this point, it would have released that 100 photons, but in this case, it has come down to a lower energy level. So there will be some additional energy which it would be releasing. So what is that energy? In the previous case, if you see, we have found out that this energy which is being retained, it is 20 photons. So herein, when it is trying to cover back from n1 to n0, that means it will again release another 20 photons. Are you getting my point? So here it was 80 because we were having 100 minus 20. So here it is becoming 100 plus 20. So this delta E, if we consider this delta E as a delta E, which is basically the energy between the two energy levels, either in the first case or in the second case, either it is that energy is being subtracted or it is being added to the system. Okay, and when this is happening, we get another Stokes line. Now this Stokes line, the anti-Stokes line, sorry, we get another line which is called anti-Stokes line, and it is on the positive half of the original frequency. Okay, now herein the Stokes shift and the anti-Stokes shift, I am abbreviating it as anti-Stokes as AS. So the Stokes shift and the anti-Stokes shift, they are having equal width. They will be appearing at the same location as compared to the Rayleigh scattering. Okay. Now herein, if you see Raman shift, it has been given over here. It is positively given, and over here it is negatively given. This is just a matter of assigning some this value. So what they are doing usually when we do it, uh, we discuss it in the form of say uh, in a positive way. That means energy is being decreased. Okay, so E minus of delta E. Okay, over here we are considering this minus is basically this positive E. So that's why they have given it as positive number, and over here it becomes E minus of minus delta E, which becomes positive, and hence you are finding it as minus numbers. Okay, so don't get confused. You just keep it in mind from here, from wavelength, and from wavelength we will be going to the frequency. As I have already told, frequency on the left hand side it will be low energy or the low frequency, and on the right hand side it will be high energy. Similarly, it would be also for the Raman shifts also. Okay. So, in other words, if you see from high to low, you are going. Now, over here, what is happening? See, we are calculating the shift, whatever the this relic scattering frequency is there, we are taking it as the zero value. We are taking it as the zero value, and against this zero value, we are calculating or we are measuring this uh, what you call Raman shift or Raman lines. Okay, Stokes line or the Raman anti-Stokes lines we are getting. Okay, so as I told you, Raman effect, it is based on the scattering of light, which includes both elastic, which is the relic scattering that occurs at the same wavelength at the incident light, and inelastic scatter, which is called the Raman scatter at different wavelengths, which will be dependent on the energy levels. And what are the energy levels? I have discussed that in Raman we are having both rotational and vibrational energies. Okay, both rotational and vibrational energies. And as I have already told you that in Raman scattering we are having this molecular bond vibrations. We are having molecular bond vibration. It is not an electronic transition of energies. Do you have any question for me? Because understanding this concept is very important for you guys. Are you guys there?
Yes, sir.
Yes, sir.
Yeah. Have you
Yes,
guys
sir.
understood?
Yes,
Okay.
sir.
Okay. Good. Now, if you see, have given the virtual energy states and all these things, whatever I have discussed till now, it is a two photon process. One photon, it is being absorbed, and secondly, another photon, it is being released. Okay, so that's why it is called a two photon process. Okay, and in this case, we have shown it in using the vibrational energy states. Say, due to the infrared absorption, in this case in the anti-Stokes Raman scattering, the molecule goes from zero level to level 1, and from there it goes to the virtual energy state, and from there it comes back to the ground level, and in that case you will be getting the anti-Stokes Raman scattering. Okay, in many ways you will find that the Raman scattering, it is being associated with IR spectroscopy. It is being associated with IR spectroscopy. Okay. Now in IR spectroscopy, as we will learn later on, that IR spectroscopy is sensitive to the heteronuclear functional group vibrations and polar bonds. Okay, especially OH stretching in water. Okay, so in many cases, while you are analyzing biological samples, you will find that there is a what you call very strong peak which are associated with the water molecules when you are analyzing any biological samples. by IR spectroscopy. Are you getting my point? So this is one of the disadvantages of using IR spectroscopy for the biological samples. In such cases, Raman spectroscopy, it comes to our savior, and Raman spectroscopy, it is sensitive to homonuclear molecular bonds. Homonuclear means same type of nucleuses, like here CC bonds, C double C bond, C triple C bonds. Like this, if you are having any homonuclear molecular bonds, then you will find that in that case you will find that Raman spectroscopy is very useful. And in biological samples, if you see, what is the constituent of our human body? The constituent of our human body is carbon, and you will find a lot of C-C, and there is always a change in the environments, and due to this reason, analysis of the biological samples, you will get more information if you perform Raman spectroscopy. Okay. However, there is a disadvantage of the Raman spectroscopy. What is the disadvantage? If you see, we are dealing with a very small amount of energy. Okay. And when we are dealing with very small amounts of energy, that means detection would be a challenge. Okay. On the other hand, in IR spectroscopy, you can easily detect the signals, and hence you need very sensitive detectors. You need very sensitive detectors in Raman spectroscopy. Okay. Now let's look over here, schematic representation of a Raman spectroscope. Okay. So what happens over here? We have a laser, then we have a lens, then we are having this sample which is there, then we are having a filter, and then after this filter there is a monochromator also. Yeah, monochromator, not monochromator, but this wavelength decomposition unit. These grating units are there, and then that decomposed spectra, it is being captured by the CCD camera to get the spectrum. Okay. Now, what should be the characteristics of this filter? Can anyone tell me? Can anyone tell me what should be the characteristics of this filter? So, what should be the
Yes.
characteristics of this filter? If you have understood all the concept, you should be able to tell me. No one? The thing is that, see, your laser is here, right? And your detector is over here in the straight line. That means you will be getting a very strong signal over here at the laser frequency mu 0, and I have told you that this laser, it will be having a very high energy or high intensity, right? Now if the intensity is very high, and as I told you, the Raman scatters, they are weak signals, then what you need to do? Any idea? No? No one can tell me? No guess? No guesses? You need to block this laser frequency. You need to block this laser frequency. So the filter should be such that it blocks the frequency of the laser which we are using. Okay, which we are using. So it is basically a kind of optical notch filter. Optical notch filter. Okay. There is another way. There is another way over here to stop this filter, to stop the laser frequency, and that is to use a polarizer analyzer set. This is the polarizer analyzer. So it is being put in a cross polarized direction. So suppose all this after this first one you get a polarized light, and this second one it will stop all these lights which are coming out in a particular direction through the through the polarizer. Okay, and analyzer, it will only allow the lights which are in different directions, because we have put it in a cross polarized condition. Okay, so apart from the laser lens characteristics, we will be able to capture the scattered lights, and the direct light from the laser would be totally blocked. Okay, so now with this I will stop today. So if you have any questions, I can answer. If you guys do not have any question, then okay, I will stop over here.